Hello and welcome to ENGR 330 Fluid Mechanics Recitation on Chapter 3. I am Dr. Krishna Pakala and I'll be helping you solve some problems based on the lectures we covered so that we can better understand the concepts. Let's look at a problem which is problem 2 from your book, Chapter 3. The given air flows steadily along a streamline from point 1 to point 2 with negligible viscous effects. The following conditions are measured. You're given at point 1 a z, a p, and at point 2 you're given a z, a p, and a velocity which is 0. And you're asked to determine the velocity at point 1. We know that in this chapter till now we learned the Bernoulli equation which can be applied along a streamline for a steady flow, incompressible, and it can only be applied along a streamline. So this problem, the statement is ideal for us to apply the Bernoulli equation. So if I were to represent this, so let's say this is my streamline, okay, and let's denote this is point 1, this denote as point 2, okay. So we're given z, we're given a p, which is 0 kilopascals. We're given, we know we have to have a velocity there, but we don't know yet because we have to find that. Z2 at point 2 is 10 meters. P2 we know is 20 Newton per meter square. And the velocity at 2 is 0. So we decided that we can apply the Bernoulli equation because of the steady airflow, negligible viscous effects, and we can apply it along the streamline. So we're talking about the fluid, which is air, so you can determine the density, standard conditions for air, specific weight for air in SI units, and all of these you can determine from your tables from the front of the book. So these are the tables which you look up, and for air you can see table 1.7, and since we're talking about SI units, so this is where I got my specific weight and density from. Okay? Alright, so now let's apply the Bernoulli equation. From point 1 to point 2 along a streamline. Let's write the general Bernoulli equation first. So the pressure plus half rho v square plus gamma z is constant, and make sure you know that it is constant along a streamline. Okay, so I can go ahead and write this for our system here for Bernoulli equation along this streamline going from 1 to 2. So I can write P1 plus half rho V1 square, and rho here is rho air, plus gamma Z1 equals P2 plus half rho V2 square plus gamma Z2. Okay, so P1 is 0. We're after V1. We know gamma, we know Z1, so this is known. We know P2. We know V2 and it's 0, so we can neglect that. And we know Z2 and gamma. So if you see here, we have one equation, one unknown, which is V1. Okay, so you can punch in your numbers in your calculator and you should get V1 to be 13.73 meters per second. So this is the application of the Bernoulli equation along the flow along the streamline. Let's look at another problem. So here we are given air flows along a horizontal curved streamline with a 20 feet radius with a speed of 100 feet per second. We are asked to determine the pressure gradient along, or in this case it would be normal to the streamline. That's what you're asked for. So let's try to represent how this streamline would look like. Okay, so the flow is like that, and it's V. We're given it's 100 feet per second. You know that it's again air, so you know the density of air, and we're talking about feet, so make sure you pick the correct units, which is the British units. Okay, so I get slugs per cubic feet. Okay, and then you're given a radius of curvature r, which is 20 feet. Okay, and the normal for this flow across this streamline would be this. I represent with an n, so this is your normal. Okay, so we learned that pressure gradient normal to a streamline for an inviscid flow in the absence of gravity. So the way I can write a general form of that and this you can find from page 108, which is equation 310a. So let's look at whether we know some of these terms can be neglected. Let's look at this one, dz over dn. So if you look at this normal, we are on a flat surface, and no matter where we are on this, z is always the same. So the difference or the gradient of z with respect to n will be 0. Okay, so there we have it. So we are after the gradient along the normal, which is this one. So this is what we are trying to find. We know the density of air, we know the velocity of air, and we know the radius of curvature. Okay, so if you were to do that, so it would be negative 2.38 10 power minus 3 over 20 feet, and the units of your density are slugs per cubic feet into the velocity square times feet square second square. Okay, and you see that we want the gradient of pressure, and pressure typically we represent in pound per square feet in this case. So we still have a slug here, but there is a relation for us relating the pound and the slug. 1 pound is 1 slug times feet over second square. So you can utilize this fact. You can do a little bit of math here where you have to multiply by a feet and a feet. I'll let you explore that. You should end up with negative 1.19 pound per cubic feet. And the reason you end up with cubic feet is you see that pressure, the units would be pound per square feet. You have a length scale here, which will be feet in this case, so that's why you end up with an extra feet. So this is the right units. Okay, so this is how you can compute the pressure gradient normal to a streamline. Let's look at another interesting problem, and I'm sure all of us have flown an airplane before. When an airplane is flying 200 miles per hour at 5,000 feet altitude in a standard atmosphere, the air velocity at a certain point on the wing is 273 miles per hour, and this is relative to the airplane. You're asked what suction pressure is developed on the wing at this point where you're given a velocity, and also what would be the pressure at the leading edge, which happens to be the stagnation point of the wing. So let's draw a cute little wing here, like an airfoil. Okay, so this is my airfoil. I know some information here, I know some information here, I know some information here. Let me represent this is point 1, this is point 2, and this is point 3. So if I were to draw a streamline, it would look something like that. Okay, you see that at point 3 would be your stagnation point. So we know that air is flowing at a velocity of 200 miles per hour and the elevation is 5,000 feet. And this is very important to know because we need to get the correct density of air at this altitude, which we can determine from table C1. So if you look at for 5,000 feet, the density is 2.048 into 10 to the minus 3 slugs per cubic feet. Okay, so make sure you use the correct density. Even the density doesn't change that much, but we have the tables, why not use them? Okay, so you can determine the density from table C1, and this is what we end up with. Okay, so let's write what we know at point 1. We know that pressure is 0 gauge, V1 is 200 miles per hour, Z1 is 5,000 feet, and at 2 we are asked to find P, so let's put a question mark there, and we know the velocity there, so it's 273 miles per hour. We know the elevation. For all intensive purposes, the elevation I'm considering to be same, even though you can have some height difference here, but compared to the actual height, you can neglect the elevation effects, and you'll see why and how that goes away later. And again, at 3, even though it is a stagnation point, you have a pressure associated with it, which would be your pressure at that leading edge, which is at 3. And we know for a fact that the stagnation point, the velocity is 0. And again, just to make sure you know it, so we also have an elevation at C3, which is the same. Okay? Alright, so now you can do this several ways, I guess. You can first try to apply a Bernoulli equation, since this is a great candidate to apply. Steady flow, incompressible, so you can apply from 1 to 3, 3 to 2, or 1 to 2. Let's see how we're gonna go with this. So what I'm going to do is, first I'm going to apply the Bernoulli equation going from point 1 to point 2. Because you see that between these guys, the only unknown would be P2, and I'll come up with one equation so I can easily solve for P2. So if I do that, so I can write P1 plus half rho V1 squared, and rho here is density of air, gamma Z1, again gamma is for air, which you can determine, and you'll see that even though you don't know that at this point, the gamma, it will go away, and we'll see why that is. You already know that P1 is 0, and the difference between these two guys would be 0, so I can neglect those. Okay, so I know V1, I know V2, so I'm after P2. If you do the math, let me write a general symbolic form for this. So this would be your equation for P2. Make sure before you plug in your numbers, convert the velocities from miles per hour to feet per second, and the tables 1.3 and 1.4 in your book at the back will have these conversion units. Use the appropriate units, and you should get P2 to be, which is in gauge, will be negative 76.43 pound per square feet. Okay, so we determined the suction pressure at point 2. Now the second part to the question is we're asked to determine the pressure at 3. So if you look up again what we have here, if you look for a streamline going from 1 to 3, you have only one unknown, which is P3, so we can easily solve that. Okay, so I can write P1 plus half rho V1 square gamma Z1 equals P3 plus half rho V3 square plus gamma Z3. Again, this difference between these guys will be 0. We know that P1 is 0. We already know V1. We know that V3 is 0 since it's stagnation point. So we can find P3. P3 gauge will be nothing but half rho of air V1 square. And if you punch in the numbers in the calculator, you should get 88 pound per square feet. So you already see that Bernoulli equation is such a simple thing. You can easily apply it. It's just that you want to know where you want to apply based on what you're asked to find. Okay, and then before you jump in and apply the Bernoulli equation, make sure the problem statement satisfies all the conditions for you to apply the Bernoulli equation. Let's look at another interesting problem. Given a Borden type pressure gauge is used to measure the pressure from a pitot tube attached to the leading edge of an airplane wing. The gauge is calibrated to read in miles per hour at standard sea level conditions rather than the usual conventional PSI, pounds per square inch. So the airspeed meter indicates 150 miles per hour when flying at an altitude of 10,000 feet. You're asked to evaluate what would be its true airspeed. Let's now again quickly draw our cute little airfoil. Okay. So I know there is a airflow at some velocity and you have the leading edge or the stagnation point there. So I know that P1 is 0 gauge. I don't know V1 yet, but I know Z1 is 10,000 feet. I don't know P2, but I know the stagnation point, the velocity is 0, and I know that the elevation is the same. Okay. So let's see what we end up with if we were to compute the Bernoulli equation along the streamline going from 1 to 2. So if I do that, I get P1 plus half rho V1 square plus gamma Z1 equals P2 plus half rho V2 square plus gamma Z2. Again, the difference between these guys will be 0, so I'm going to ignore that. P1 is 0, and I know that V2 will be 0. So I don't know V1 and I don't know P2, but I can come up with a relation between these two. Okay. So you're given an information that the gauge reads 150 miles per hour, which is being calibrated at sea level. Then we can compute the density of air from table C1 for sea level, which is 2.377 into 10 to the minus 3 slugs per cubic feet, and see what would that transpire in terms of the pressure. Okay, so make sure you convert your velocity from miles per hour to feet per second. So I would get 57.5 pound per square feet. Okay. Now let's see at 10,000 feet and for a density of air which you have to compute from the table C1. For 10,000 feet it's 1.756 10 to the minus 3 slugs per cubic feet. So you have that there. You want to evaluate what velocity you would read. Okay, so I have 57.5 pound per square feet, which is P1, or sorry, it's the equivalent of pressure, which is right at sea level, should be equal to half times the density at 10,000 feet times V1 square. Okay, so if I put in these numbers, I would get about 256 feet per second, or about 174.55 miles per hour. So this will be your true air speed. Okay, so till now all we had to use was one equation, which was the Bernoulli equation along a streamline. We also learned that in some situations we might have to use another equation which we learned in class, which is the conservation of mass. For a steady flow, you know that Q equals area times velocity, the flow rate. So if you have steady flow at 2 points, 1 and 2, Q1 should be equal to Q2. So let's look at a problem where we might have to use that in the future, but I'm just telling you that in some instances we have to use that. Let's look at 334. Given streams of water from two tanks, these two tanks here, impinge upon each other as shown, and if the viscous effects are negligible and point A is your stagnation point, you're asked to determine this height h. Okay? So before we do that, let's identify certain points on the flow field where we can apply the Bernoulli equation. Let me represent, since the pressure is given here, let me represent this point as 1, and we already have A, let's denote it as A itself, and let's denote this point here as 2. Okay? Alright, so let's write the Bernoulli equation along a streamline going from 1 to the point A. So PA plus half rho VA square plus gamma ZA will be equal to P1 plus half rho V1 square plus gamma Z1. Okay. So for a fact, we know that VA will be 0, it's a stagnation point. We know that for a large tank, you can neglect V1. So V1 is 0. And so your only unknown in this case would be PA. There are several ways to compute H, but if you're ever asked to find the pressure at A, you can do it this way. So pressure at A will be 25 psi plus gamma Z1 minus ZA. Z1, if I have the datum here, this is my datum. Z1 will be 8 feet. ZA is 20 feet. Make sure you convert them to inches, whichever units you prefer. So you should end up with PA to be 19.8 psi, pounds per square inch. So now that we know that, we can probably try to draw a streamline going from 2 to A and apply our Bernoulli equation. And you see that the only unknown would be this height h there. So we'll see how that happens. So you have PA plus half rho VA square plus gamma ZA equals P2 plus half rho V2 square plus gamma Z2. Again, we know that VA is 0. We know that P2 is 0 gauge right here. V2 for a large tank, you can neglect the change in velocity or the change in this height. So V2 would be 0. So I can write PA, which we computed just now, plus gamma ZA equals gamma Z2. Okay. So if you do this, if you simplify this, you'd end up with in ZA is 20 feet, but Z2 is 20 plus H if I pick this as datum. So you see how H props up. The general symbolic relation you'd end up with this. H equals PA over gamma, and H turns out to be 45.7 feet, or if you're interested in inches, it's 548.31 inches. Okay. You could have actually done this in a different way where you don't have to compute PA. You can write PA in terms of other variables, but this is one way to do the same problem. Okay. Now let's look at a problem where the conservation of mass, which I was talking about earlier, could be applied. So water flows steadily in this problem 344 through the large tanks shown in the figure. You're asked to determine the water depth HA. So at first, let's see what it means by a steady flow. So immediately you can recognize that Q2 will be equals to Q4. Q2, whatever coming in here should be going out here, and maybe I should represent what I mean by Q2 and Q4. Let me pick this as number 1, this point as number 2, this point as number 3, and the free stream flow here as number 4. Now you can see that Q2 will be equal to Q4. Whatever is coming in should be going out. And in general, the flow rate will be area times the velocity. Okay. So if I were to compute Q4, I can write this as A4 V4. Okay. I know I can determine A4 because I know the diameter of the pipe there, but I don't know V4, but this is where Bernoulli equation can help us. So if I want to apply the Bernoulli equation going from 3 to 4, since it seems that I know a height, I know almost all the parameters except V4, so I guess I'm going to be good there in terms of having one equation and one unknown. Let's see that. So P3 plus half rho V3 square plus gamma Z3 equals P4 plus half rho V4 square plus gamma Z4. Okay. P3 is 0, gauge atmospheric. V3 is 0, large tanks. Again, the flow rate is also steady. P4 is again 0, gauge. So you can see that you can compute V4. If you do a little bit of algebra, it happens to be 2G times Z3 minus Z4 under the square root sign. So you don't have to necessarily pick a datum because Z3 minus Z4, you already know that it is HB, so it's 2 meters. So if you put in the numbers, you should get 6.26 meter per second. Okay. Similarly, I can now determine Q4. It would be pi d square over 4 times 6.26. So I end up with 0.013 meters cubed per second. Okay. All right. So now we can probably apply the Bernoulli equation again, going from point 1 to point 2 along that streamline. So P1 plus half rho V1 square plus gamma Z1 equals P2 plus half rho V2 square plus gamma Z2. P1 is 0, V1 is 0, P2 is 0 gauge. So you can compute V2, which would be square root of 2G Z1 minus Z2. And you can see from the figure that Z1 minus Z2 is nothing but your height HA. Okay? However, we don't know V2, right? However, we know that Q2 is Q4. That would mean A2 V2 equals A4 V4. So we know A2. We can substitute V2, which will have only one unknown, which is H. We know A4 and we know V4, which we computed earlier. So that we end up with an equation with one unknown. So I can write this as pi over 4 t square 2g HA under the square root sign equals to the flow rate. So I can determine HA to be 15.4 meters. So here is a problem where you have to apply the conservation of mass in addition to the Bernoulli equation. Let's look at another problem. So water in this figure is siphoned from a tank as shown. You're asked to determine the flow rate and the pressure at point A, which is a stagnation point. As soon as this water hits the surface here, the tank, it happens to be the stagnation point, so the velocity there would be 0. Okay, let's identify some points here so that we can probably apply the Bernoulli's, and also maybe we have to use the conservation of mass here since we are talking about flow rates. So let's pick this as A, which we already have, and let me pick this as point 2. Okay. All right. So if I were to draw a streamline going along this from 1 to 2, okay, I can probably determine what is the exit velocity here, V2. Let's see. So I have P1 plus half rho V1 square plus gamma Z1 equals P2 plus half rho V2 square plus gamma Z2. So we know P1 is 0 gauge. For large tanks, V1 is 0. P2 again is 0 gauge. And if we have our datum here at point 2, Z2 will be 0 and Z1 will be 3 meters going from here. Okay. So I put in those. Now you see that I have only one unknown, okay, which is V2. I know the rest of the stuff. So it is just square root of 2g V1, and you should get that to be 7.67 meters per second. Okay. So once I know this, I know that I can compute a flow rate. So Q, which would be nothing but, or Q2, it would be the same, A2, V2. I know A2. I know the diameter of the pipe. It's the same diameter throughout. So I have pi over 4 d square times the velocity. So that gives me 9.64 into 10 to the minus 3 cubic meter per second. Okay. However, we are not done yet with the problem. Only we determine the flow rate. We still have to determine the pressure at point A. This you can now do by drawing a straight line going from 1 to A. Okay. So if I apply the Bernoulli equation going from 1 to A for a streamline along that streamline, we get P1 plus half rho V1 square gamma Z1 equals PA, which is where we are after, half rho VA square plus gamma ZA. Again, if I pick the datum here, ZA is gone, VA is stagnation point, so velocity is 0. After PA, I know Z1, okay, which is 3 meters. V1 is 0 for a large tank, P1 is 0 gauge. So I end up with a simple relation for PA, which is gamma times Z1. Okay, so you should end up with 29.4 kilopascals. Okay. You see that Bernoulli equation and the mass conservation are so easy to apply. It's just that I want to know what things you want to find out and then make sure you have a streamline and apply the Bernoulli equation along that streamline between those 2 points. And make sure when you apply, you end up with one equation and only one unknown. Otherwise, you might have to use something else, like in conjunction with Q2 here, which we did. Okay? Let's look at another interesting problem. Problem 64. Water exits a pipe as a free jet and flows to a height h above this exit plane. As shown here, the flow is steady, incompressible, frictionless. Immediately, that would tell me that I can apply Bernoulli equation. These statements are a good candidate for a Bernoulli equation along the streamline. And you're asked to determine the height h, and you're asked to determine the velocity and pressure at section 1. Okay, let me represent this point here, the exit, as section 2. Okay, now let's look at part A, where we're asked to determine the height h. Okay. If I were to draw a streamline going from 2 to, let me represent this point here in the free stream where the jet exit shoots up to the height h as number 3. If I were to do a streamline between 2 and 3, I can probably get h. Okay, let's see if that works out. So the Bernoulli equation along 2 and 3 is P2 plus half rho V2 square plus gamma Z2 equals P3 plus half rho V3 square plus gamma Z3. Okay, P2, 0 gauge. I know V2, which is V, which is 16 feet per second. I know this. I know Z2. Okay, let's not worry about datum yet because the difference will give me that height h. P3 is again 0 gauge. V3 is again 0. So I should end up with rho V2 square over 2 is gamma Z3 minus Z2, or h will be V2 square over 2g. If you put in the numbers, h turns out to be 3.98 feet. Okay. Now let's look at part B, where we are asked to determine the velocity and the pressure at section 1. Okay. So before we jump in, since it's a steady flow, okay, the flow is steady. So going from point 1 to point 2, the flow rate has to be the same. Okay. So using that fact, I can write steady flow Q1 equals Q2, or A1 V1 should be equal to A2 V2. Right? We know V2, we know A2. Okay, make sure A2 has a different diameter and A1 is a different diameter pipe, so the areas will be different. So we are after V1, we have one equation, one unknown, so we can easily solve this. So I can write V1 equals A2 over A1 times V2. If I put in the numbers or the variables here, the pi over 4's cancel each other, so I'm not putting them here. So you should end up with 36 feet per second. Okay. And you'll see why I had to do this. First find V2. This you're asked to find in the first point, but also you have to find that if you have to find the pressure at 1. Otherwise you'll end up with one equation and two unknowns. Okay? So the problem kind of led you to it. So P1, if I want to draw a streamline going from 1 to 2, I can write a Bernoulli equation along that streamline, okay, which will be that. Okay. So I know P2 is 0. Okay. I know I want to find P1. Okay. I know V1, which we just found out, or which we just found out, that's right. I should probably write this in a better way. Okay, so V1 is A2 over A1 times V2, D2, D1. So this should be V2 multiplied, okay, and this is what we are after, V1. Okay, all right. You can do this, and I just had a small multiplication sign missing there. Okay, so that's what. So we have V1, and I know V2, which is 16 feet per second. I know the Z1, Z2 difference, which is 8 feet. Okay, this height is 8 feet, the difference between these guys. So you don't necessarily have to pick a datum here. It'll all work out. Okay, so you see that our only unknown is P1. Okay, so P1 will be half rho V2 square minus V1 square plus gamma Z2 minus Z1. Okay, if you put in the numbers and make sure you have consistent units, so you should end up with negative 509.6 pound per square feet. Okay, so this concludes the session of chapter 3, where we looked at Bernoulli equation, where we looked at conservation of mass, and we looked at some problems where we can apply the two facts we learned. And we'll continue with some more problems pretty soon. Looking forward to helping you all again. Make sure you give these videos a good chance to sink in and try these problems, and it should help you with the homeworks and also with learning the material in a better way. Thank you.